Something out there just changed the equation. For months we've been tracking 3I Atlas, the interstellar visitor passing through our solar system on a trajectory that seemed predictable and safe. Most of us thought it was just another comet, another fascinating piece of debris from somewhere beyond our sun travelling through the darkness, another data point in the cosmic survey, another piece of interstellar archaeology delivered to our doorstep by the mechanics of celestial dynamics and orbital interactions. The object itself is fascinating from a scientific perspective. An interstellar comet, a piece of a distant planetary system. These are rare. We've only ever confirmed 3 of these objects, but increasingly rare observations become increasingly valuable to our understanding. But new calculations, refined observations, and a mounting body of evidence suggest we might have been looking at this situation all wrong. We might have been misunderstanding the actual dynamics. 3I Atlas isn't just passing by anymore according to some analysis. The trajectory is shifting subtly. The acceleration is continuing rather than fading. And according to some of the world's sharpest astronomers and researchers, if the current vectors hold, if the non-gravitational forces keep pushing in the same direction, if the patterns we're observing continue unabated, the object could be on course to reach Earth's vicinity by late 2025. Not an impact necessarily. The margins are still vast, the distance is still enormous. We're not talking about collision scenarios here, at least not in the immediate sense. But we're talking about something significant enough that it's forcing researchers to reconsider their models, re-examine their assumptions, and ask questions that most of them wouldn't have entertained just a few weeks ago. We need to talk about what's actually happening and why the narrative around this object has changed so dramatically in just the past few weeks. The story has shifted from a simple scientific observation to something far more complex and contested and fragmented across different interpretive frameworks. If this resonates with you, if you're curious about what's really out there and what we might be missing, smash that like button and subscribe, because we're diving deep into something that most of the mainstream media isn't covering properly. Not because they can't understand it, but because understanding it requires patience and nuance and complexity, and they're not structurally built for that kind of engagement. Drop a comment about where you're watching from and what you think is really going on with this object. The signal only spreads if we push it together, so thank you for being part of this investigation and this search for understanding. Now let's get into what the data actually show and why some astronomers are reconsidering everything they thought they knew about this object and its trajectory. Because the data is real. The measurements are solid. The observations were conducted by reputable facilities with rigorous protocols. But the interpretation, that's where things get interesting and contentious and fragmented. That's where science becomes art in a sense, where experience and intuition meet data, where different experts can look at the same numbers and draw different conclusions. The discovery that changed everything. Back in July, when 3I Atlas was first identified by the Asteroid Terrestrial Impact Last Alert System in Chile, it seemed straightforward enough on the surface. Another interstellar visitor. The third confirmed object we'd ever detected coming from beyond our solar system. Just another wanderer passing through the neighbourhood. A hyperbolic trajectory meant it was just passing through, unbound to our sun, destined to drift back into the void between stars after its brief visit to our cosmic neighbourhood. The object wouldn't linger. It would continue on the path it had been following for millions of years. The discovery itself wasn't controversial. This was solid astronomy. Rigorous observation. The kind of work that happens all the time in modern sky surveys conducted by automated telescope systems designed to catch anything unusual or unexpected. Teams of astronomers around the world started collecting data almost immediately. The notification went out to observatories everywhere. The James Webb Space Telescope was tasked with observations. Hubble got pointed in the right direction. Ground-based observatories in Chile, Hawaii, and elsewhere coordinated their efforts. Radio telescopes joined the campaign. The coordination was impressive, really quite remarkable. The mobilization of resources reflecting how seriously the astronomical community takes new interstellar visitors. This wasn't routine observation. This was priority observation time. This was significant expense and effort. By October, when 3I Atlas reached perihelion, its closest point to the Sun, we had accumulated a reasonably comprehensive picture of what we were looking at and what we were actually dealing with here. A massive object, potentially several kilometers across in its largest dimension. Some estimates suggested 5 kilometers or even more in diameter. Estimates place the mass in the tens of billions of tons, quite possibly higher. A mountain, a small world. The composition was unusual, showing higher concentrations of certain carbon compounds than we typically see in solar system comets, suggesting it formed under different conditions in a different star system. Different stellar environment, different chemical processes, different physics acting on the material during formation. The colour was off too, bluer than expected, significantly bluer. Typically comets appear reddish or greyish or brown because their composition includes dark organic compounds and processed material accumulated over billions of years. This object showed a blue tint that was striking and unusual, possibly indicating ionized carbon monoxide molecules in its atmosphere, or perhaps something else we hadn't quite figured out yet. The spectroscopy was ambiguous and contradictory. Some lines of evidence pointed one direction. Other measurements suggested something different. That ambiguity is interesting because it forces careful follow-up work. The initial data suggested a straightforward comet, albeit an interesting one. Unusual but not unprecedented. But then the anomalies started appearing. Observers noted something unexpected in the astrometric data. The object wasn't precisely where gravity alone should have placed it. There was an offset, small but measurable, about 4 arc-seconds of deviation from the predicted path. That doesn't sound like much until you're actually tracking something across millions of kilometers of space and trying to predict where it will be weeks in advance. An error at that scale demands explanation. Non-gravitational forces were at work. Something was pushing the object. The most obvious candidate was outgassing. Comets do this constantly all the time. As they approach the sun and get heated, ices on the surface sublimate, turning directly from solid to gas without passing through a liquid phase, and that escaping material creates thrust, a rocket effect on a small scale but measurable nonetheless. Avi Loeb, the controversial Harvard astrophysicist who'd previously raised questions about the artificial nature of Oumuamua years ago, ran the calculations. If the observed acceleration was being caused by natural outgassing, he determined that roughly 1/6 of the object's total mass would need to evaporate over the course of about a month to produce the observed effect. 1/6, a substantial fraction. That's not impossible. Comets are known to be variable and sometimes dramatic in their activity. Comet Shoemaker-Levy fragmented. Comets have been known to suddenly brighten or fade. But it would be visible. A mass loss on that scale should produce an enormous coma, a massive cloud of gas and dust surrounding the nucleus. Telescopes should have spotted it easily. The signal would have been unmistakable. Yet the observation showed something more subtle, more ambiguous. There were reports of jet structures, possibly directed toward the sun in an unusual configuration. That's strange because typically jets point away from the sun. There was the blue coloration. But a giant visible coma proportional to that theoretical mass loss rate. That hadn't been definitively observed. The expected signature was missing. The dust and gas we should have seen weren't there in the amounts we expected. It was this discrepancy between expectation and observation that opened the door to other explanations and new lines of questioning from researchers. It was this mismatch, this inconsistency, that changed the entire conversation around the object fundamentally. It was this moment that made some serious scientists, researchers with decades of experience and publication records, start asking uncomfortable questions about whether we were looking at a purely natural phenomenon at all. The absence of an expected phenomenon became itself a phenomenon worth studying carefully. The lack of a visible coma proportional to the calculated mass loss rate raised more questions than the presence of anomalies typically would. It violated the principle of parsimony, the idea that when we observe an effect, we should look for the simplest explanation. But the simplest explanation wasn't matching observations. It suggested that either our outgassing model was wrong or incomplete for this particular object, or something fundamentally different was going on, something we hadn't accounted for. And that uncertainty, that gap between model and observation, is where the interesting science lives. That's where new discoveries get made. But it's also where speculation can run wild if we're not careful about distinguishing between data and interpretation. Trajectory revision. The numbers don't lie. Here's where things get interesting and where the mathematics starts to matter more than the mystery. Where calculations become more important than speculation. Where we have to actually work through the physics carefully. The original trajectory calculations for 3I Atlas showed it passing Earth at a comfortable distance of approximately 1.8 astronomical units on December 19, 2025. An astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. So we were talking about a missed distance of around 270 million kilometers. To put that in perspective, the Moon is 384,000 kilometers from Earth. This object would pass at a distance equivalent to roughly 700 times the Earth-Moon distance. In planetary defense terms, that's extremely safe. Objects are considered potentially hazardous if they pass within 0.05 astronomical units of Earth, about 7.5 million kilometers. This object was going to pass at 30 times that safety threshold. NASA said no threat. The European Space Agency said no threat. The International Astronomical Union had no concerns. All the official channels confirmed we were looking at a distant flyby, nothing more. But then the trajectory refinement started coming in. As more observational data accumulated, as teams refined their orbital calculations and accounted for various perturbations and influences, something subtle began to shift. Not dramatically, not in ways that would trigger alarm bells at space agencies, but enough that researchers started updating their models. The acceleration data kept coming in consistent and repeated and verified by multiple independent observatories. The Jet Propulsion Laboratory was tracking it. The European Southern Observatory was tracking it. Ground-based facilities around the world contributed astrometric data. The object was not following a purely gravitational path, it was being accelerated in ways that required explanation. If the acceleration was continuing unabated, if it persisted even as the object moved away from the Sun, that meant the normal outgassing explanation was straining under the weight of the evidence. Something else was going on. An independent researcher on social media ran the arithmetic, and it spread like wildfire through Reddit and Twitter and YouTube comments. If 3i Atlas sustained an acceleration of 0.02 mm per second squared for 50 days, the velocity change would be approximately 86 meters per second. That's straightforward kinematics. Acceleration times time equals change in velocity. 50 days is 4.32 million seconds. Multiply by 0.02 millimeters per second squared, and you get 86.4 meters per second. That's a delta V, a change in velocity, that could theoretically alter the trajectory significantly. Point it in the right direction at the right time, and that kind of velocity change could shift the miss distance by hundreds of thousands of kilometers. It could change when the object crosses Earth's orbital plane. It could change the geometry of the approach. It could transform a distant flyby into something closer, much closer. The math itself was correct. Absolutely correct. No dispute there whatsoever. Anyone with a calculator and a basic understanding of simple arithmetic could verify it themselves. The velocity change calculation was straightforward physics, basic kinematics from a first-year undergraduate physics course. The formula is simple. Change in velocity equals acceleration times time. But here's the crucial thing. Here's where assumption starts layering on top of observation in ways that can subtly shift the entire conclusion. The calculation assumed the acceleration continued uninterrupted for 50 days. We don't actually know that. Acceleration due to outgassing typically varies with distance from the Sun. As the object moves away, solar heating decreases, sublimation slows, thrust diminishes. The calculation assumed the acceleration was being applied in the optimal direction for moving the object toward Earth. We don't know that either. The direction of any non-gravitational force matters enormously. A push to the side doesn't bring the object closer. A push in the wrong direction moves it away. It assumed Earth would be in the right position when the object reached the crossing point. Earth moves about 30 kilometers per second in its orbit. It covers vast distances in days. The assumptions multiplied, and with each one, the confidence in the final conclusion diminished noticeably. This is how propagation of uncertainty works in orbital mechanics. You start with measurements that have error bars. You use those measurements to calculate velocities with error bars. You integrate forward in time to predict positions with error bars that grow larger the further ahead. You project. Each assumption compounds the uncertainty. NASA released updated trajectory calculations showing no significant change to the miss distance despite the acceleration data. The object was still going to pass Earth at a safe distance according to their models. The official calculations incorporated all the perturbations, all the known forces, all the uncertainties properly accounted for in their mathematical models. They factored in solar radiation pressure, planetary gravity, relativistic effects, all the physics we understand well, but the discrepancy between the official calculations and the social media narrative created exactly the kind of uncertainty that fuels speculation and public division. Which calculations were more accurate? What data were the official agencies considering in their analyses? Were they being transparent with the public about their assumptions? Or were they downplaying something to avoid panic or unnecessary alarm? The narrative shifted from straightforward scientific observation to something far more contentious, more dramatic, more prone to interpretation and reinterpretation by different groups. The distance to impact scenario, the misdistance calculations, these fundamental parameters began to feel less settled, less certain in the public mind. When two different communities of experts are publishing different numbers from different models, when official agencies say one thing and independent researchers running their own calculations say another, that's when public confidence in the process fractures and divides. That's when people start wondering who's right, and whether anyone is being completely transparent about what they actually know versus what they're assuming or predicting based on limited data. What we know about interstellar visitors. Before we dive deeper into what 3i Atlas might be doing and what trajectory it might be following, we need to understand what we're actually dealing with here. This is only the third confirmed interstellar object we've ever detected in human history. Let that sink in for a moment. Out of billions of objects in our solar system that we've catalogued and studied, only 3 have been confirmed as coming from beyond our Sun, from interstellar space, from different star systems. The first was Oumuamua, discovered in October 2017 by the Pan-STARRS Survey Telescope in Hawaii. It was a genuinely strange one from the very beginning of observations, elongated, distinctly cigar-shaped, roughly 10 times longer than it was wide. It showed unexpected acceleration as it moved away from the Sun, deviating from what gravity alone should have produced. The acceleration didn't match what gravity alone should produce. Some scientists proposed it might be a light sail, a thin reflective sheet pushed by solar radiation from the Sun. That interpretation captured public imagination. Most colleagues dismissed that interpretation as too speculative, too fantastic. They argued instead for a natural comet with unusual properties, maybe composed of nitrogen ice that sublimates without leaving a visible cloud. The debate was fierce, and it never quite resolved to everyone's satisfaction. There's still disagreement in the literature about what Oumuamua really was. Then came Borisov in 2019, discovered by amateur astronomer Gennady Borisov. This one looked like a normal comet. Coma visible around the nucleus, tail present and streaming away from the Sun, spectroscopy revealed water and carbon monoxide, all the classic signatures of an icy body being heated by solar radiation and vaporizing. In many ways, Borisov was reassuring. It showed that not every interstellar visitor had to be a mystery or an anomaly. Some could be perfectly explicable using conventional comet physics and models we already understood. Natural comets from another star system, nothing more. Now we have 3i Atlas discovered on July 1st, 2025, and it falls somewhere between those two extremes. It shows some comet-like features, but also characteristics that don't fit neatly into standard models. The composition is unusual for a typical comet. The acceleration profile is strange and doesn't behave exactly like classic outgassing. The colour is off, shifted toward the blue rather than the red or grey we expect. The possible jet structure directed toward the Sun rather than away from it as physics would dictate. Every interstellar object we've detected has taught us something important and new about the diversity of bodies that exist in the galaxy beyond our solar system. They're messengers from different star systems, carrying information encoded in their composition and behaviour and trajectory and the way they move through space. They're like message bottles drifting across the cosmic ocean. We can study them in ways we could never study the exoplanets they came from. We can gather direct samples of chemistry and physics and material that developed under completely different conditions in completely different stellar environments. That scientific value doesn't depend on whether 3i Atlas is a comet or something else. It doesn't depend on how it formed or why it's here or what cosmic process ejected it from its home system. The object itself is precious to our understanding of the universe and how planetary systems form. But the behaviour we're observing, the acceleration, the trajectory that might or might not be heading toward Earth, these details matter profoundly because they force us to confront questions about what's possible and what we can actually know about an object passing through our solar system. The history of interstellar object observations is incredibly short. We've only been detecting these things for about 8 years now. Our sample size is small. Statistical claims about patterns are essentially meaningless, with 3 confirmed objects spread across years. But every new visitor teaches us to refine our models of comet behavior and orbital mechanics. Every anomaly demands investigation because science advances through careful observation of things that don't fit expectations. Every discrepancy between prediction and observation is a potential window into physics or phenomena we haven't yet fully understood or characterized. 3i Atlas is continuing that ongoing process of discovery, forcing us to examine our assumptions and consider possibilities we might otherwise dismiss out of hand. Every discrepancy teaches us something if we're willing to look carefully and think deeply. This object, whatever it ultimately turns out to be, has already changed how we think about interstellar visitors and how we approach the problem of detecting and characterizing objects from beyond our solar system. The questions raised by 3i Atlas will inform how we study future interstellar objects and what we should look for in terms of anomalies or unexpected features. They'll change our detection protocols, our observation strategies, the way we analyze spectroscopic data. They'll force us to think more carefully about what constitutes evidence for natural versus non-natural explanations. The scientific method depends on this kind of challenge to our assumptions. Objects like 3i Atlas are gifts in a way, even if they're confusing gifts. They force us to examine whether our models are really as complete and comprehensive as we thought they were. The observation window crisis. We're in a critical period right now, possibly one of the most time-sensitive astronomical situations we've encountered in recent years. The window for observing 3i Atlas effectively is narrowing and it won't come back, not for any foreseeable human future. The object has passed its perihelion, its closest point to the Sun, which occurred around October 30th, 2025. It's now moving outbound, heading toward its closest approach to Earth on December 19th, then continuing deeper into the outer solar system beyond. After that, it's gone. The observation window is finite and rapidly closing. As the object moves away from the Sun, the solar heating that drives any outgassing decreases exponentially with the square of distance. If outgassing is what's driving the acceleration, that process should weaken significantly. Spectroscopic signatures dependent on solar heating will fade and disappear. The object will grow dimmer in visible light as it recedes. The infrared signatures that JWST can detect will diminish below detection thresholds. The brightness drops rapidly with distance. In a few weeks, maybe a few months, 3i Atlas will simply become too faint and too distant to observe effectively from Earth with any of our current technology. Radio observations might persist longer, but optical and infrared observations will fail. We'll have missed our chance to study it up close during the critical window. We'll have missed the opportunity that won't come again in our lifetime. Whatever mystery surrounds its motion, whatever questions remain about its nature and its possible intentions, those will likely remain unanswered unless we gather the critical data now, during this observation window that's literally counting down day by day. Multiple telescopes are coordinated right now in ways that rarely happen in astronomy outside of exceptionally significant events and critical moments. The resource allocation is unusual and expensive and carefully managed. The urgency is palpable even if most of the general public isn't hearing about it or understanding the deep implications of what's happening. Hubble is taking images. JWST is collecting detailed spectroscopy. Ground-based observatories are monitoring astrometry with unprecedented precision and accuracy. Radio telescopes are listening for any unusual signals at multiple frequencies. The Very Large Array in New Mexico is tracking it. Facilities in Chile are collecting data. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, will pass within 64 million kilometers of 3i Atlas on November 4th. An opportunity for additional measurements, even if it's not close enough for a dedicated scientific flyby or true encounter. Every bit of data that can be gathered is being gathered systematically and carefully. The problem is that legitimate science takes time, real science. Data has to be collected with rigorous protocols and careful methodology, reduced and processed through established procedures, analysed carefully by skilled researchers, peer-reviewed by multiple independent experts, and finally published in peer-reviewed journals for the community to scrutinise. The social media narratives spread in hours across the globe. The actual scientific results, the real findings, take weeks or months to appear through proper channels. By the time the comprehensive analysis is complete, by the time papers are written and published and findings are verified independently by other research teams, the observation window might have already closed. We might be left with incomplete data and incomplete answers to the questions raised. If the object behaves like a normal comet, if we see massive outgassing and dust clouds producing the acceleration we've measured, if spectroscopy reveals typical volatile compounds like water ice and carbon dioxide, if radio telescopes detect nothing unusual, then the natural explanation holds and the mystery resolves cleanly into straightforward physics and established comet theory. But if the observations show something different, if mass loss measurements show minimal outgassing despite the acceleration continuing, if signals are detected, if the composition is even more unusual than initial reports suggest, then we're looking at a genuine puzzle that might take years to fully understand and integrate into our models. This is the critical moment. This is when the science actually matters in concrete and measurable ways. This is when careful observation and rigorous analysis can determine whether we're dealing with an interesting but ultimately explainable natural phenomenon or something that genuinely challenges our understanding of what can exist in our solar system. The data we collect in the next few weeks and months will determine how this entire story gets resolved, or whether it remains unresolved, a genuine unsolved mystery that haunts the scientific community and the public for decades to come. That's not hyperbole or exaggeration. That's the actual reality of studying objects that appear once and then vanish into the void, never to return in our lifetime. Scientific community response. The reaction from mainstream astronomy has been measured, careful, and quite revealing about how science handles uncertainty in public communication in the modern age. The official agencies have maintained that no threat exists based on their calculations. The trajectory calculations remain consistent with a safe passage at 1.8 astronomical units on December 19th. The deviation from those predictions, while real and measurable, doesn't necessarily translate directly to an Earth intercept scenario. The required velocity change to convert the current trajectory into an actual impact would need to be far larger than 86 meters per second, unless the acceleration was applied in a very specific direction at a very specific time with incredibly precise and coordinated timing. NASA has stood by this assessment in their official statements, so has the European Space Agency in their public communications. The International Astronomical Union has been cautious, but not alarming in tone. But beneath the surface of official pronouncements, there's palpable tension within the research community. Some researchers who study interstellar objects have started revisiting previous work on Oumuamua, wondering whether they and their colleagues were too dismissive of exotic explanations. Maybe they were too quick to default to natural explanations. Avi Loeb has been outspoken about the need to consider all possibilities, including technological origins, even in the absence of definitive evidence pointing that direction. He argues this is scientifically appropriate given the limits of our understanding. That openness to unconventional thinking is valuable in science, but it also provides ammunition for sensationalism and overstatement. The mainstream media has picked up on the story, often in simplified or exaggerated forms designed to capture attention and drive engagement. Headlines scream about alien probes and potential impacts, while the actual article text is usually more measured and careful. Most people read only the headlines. They absorb the dramatic framing, and that becomes their entire understanding of the situation. The responsibility in science communication is to distinguish clearly between what the data show and what someone extrapolates from those data. What is observation versus interpretation? The data show a non-gravitational acceleration, full stop. That's fact. The extrapolation to Earth intercept, to intentional maneuvering, to alien technology, those are interpretations built on top of the data. They might be true, but they're not established facts. They're possibilities. There's a balance to strike in science communication. On one hand, we shouldn't dismiss possibilities prematurely just because they seem unlikely. Science advances by considering ideas that seem implausible at first. On the other hand, we shouldn't treat speculation as equivalent to evidence in public discourse. The claim that 3i Atlas is lining up with Earth is not on the same footing as the observation that it has non-gravitational acceleration. One is measured through telescopes. The other is inferred through calculation and assumption. The social media ecosystem has collapsed that critical distinction. Everything becomes a claim, a theory, a possibility weighted equally in the court of public opinion regardless of the evidence base. The scientific community is watching this carefully, fully aware that how they communicate about 3I Atlas will influence public trust in institutions, in expertise, in the entire process of science itself going forward. Some researchers are leaning into the mystery, acknowledging uncertainty openly, inviting speculation within appropriate bounds and proper context. Others are emphasizing the statistical improbability of various alarming scenarios, trying to ground the conversation firmly in physics and careful observation rather than drama and narrative sensationalism. Both approaches have merit and value. Both are being tested right now as this story continues to unfold simultaneously across social media, traditional news outlets, academic publications, and the scientific literature in real time. The tension between these approaches reflects something important about how modern science operates. We live in an age where information spreads instantly, where social media can amplify claims faster than peer review can evaluate them, where the narrative can move ahead of the data, and yet the fundamental work of science remains slow, methodical, careful. The astronomical community is trying to navigate this space, to communicate clearly about what's known and what's uncertain, to acknowledge the genuine mystery while not sensationalizing it. This is harder than it sounds. The stakes are high. Public understanding of science is at stake. Public trust in scientific institutions is on the line. How 3I Atlas is covered, discussed, and analysed in the coming weeks will send a message about whether we can handle genuine uncertainty and ambiguity in a world that increasingly demands definitive answers and clear conclusions presented instantly. Whether we can sit with mystery long enough for the science to actually work, to do its job, to provide real answers based on data rather than rushing to judgment. This is a test for our time, a test of whether we can be patient enough to let careful investigation proceed properly, whether we can resist the urge to resolve things instantly through social media discourse and viral narratives and incomplete information. It's a crucial test of scientific literacy and cultural maturity. How we respond will matter far beyond just this one object. Somewhere in the scientific literature right now, carefully buried in papers that only specialists will read closely, there's a growing acknowledgement that the probe hypothesis, once dismissed outright as pure science fiction fantasy, deserves serious consideration at least. Not because it's proven definitively, not because we have overwhelming evidence stacked on evidence pointing clearly toward an artificial origin, but because the alternative explanations are becoming increasingly difficult to sustain without significant stretching and creative interpretation and special circumstances. 3 Atlas keeps presenting us with characteristics and behaviours that don't fit neatly into our established models of how comets behave in the real world. And when natural explanations require more and more complicated assumptions, more and more exceptional circumstances, more and more special pleading to make the data work, that's when scientists start asking whether maybe we're missing something fundamental about what this object actually is and where it comes from. The probe hypothesis returns. The probe hypothesis isn't new, not by a long shot. Avi Loeb has been advocating for serious consideration of technological origins for interstellar objects since Oumuamua first appeared in 2017, and he's weathered significant criticism for taking that position seriously. Back then, Oumuamua's elongated shape, its lack of visible outgassing despite unexplained acceleration, and its unusual trajectory all raised questions that the mainstream scientific community treated with skepticism, bordering on outright dismissal. There was an almost reflexive resistance to even entertaining the possibility. Most astronomers preferred the natural explanation, even when the natural explanation required invoking exotic types of ice, or unusual compositions that we've never directly observed before, even when it required special pleading and circumstantial reasoning. Hydrogen ice, nitrogen ice, things we don't see in our solar system's comets. The resistance was palpable because the implications felt too large, too destabilizing to the comfortable frameworks we'd built around how the universe works. The pattern is repeating with 3 Atlas, but with some crucial differences that make it harder to dismiss out of hand. 3 Atlas isn't as extreme as Oumuamua was. It shows some normal comet characteristics that keep it grounded in the familiar, but it's also showing enough anomalies that the scientific community can't quite dismiss the possibility outright anymore. The non-gravitational acceleration we measured, the unusual composition with high carbon dioxide, and nickel content suggesting formation somewhere else entirely, the lack of proportional outgassing despite the thrust that should accompany it. the blue coloration suggesting ionized carbon monoxide. Individually, each of these can be explained through natural processes. Each one has a plausible explanation if you look at it in isolation. But together, when you step back and look at the whole picture, they paint a portrait that doesn't quite fit standard comet behavior. The constellation of anomalies becomes harder to dismiss. What would a probe look like if it visited our solar system? This is the question Loeb has posed repeatedly, and it's deceptively challenging. Loeb has argued that an advanced civilization sending exploratory probes across interstellar distances might deliberately design them to appear like natural objects. A probe disguised as a comet would draw less attention, would be less likely to trigger defensive responses from a civilization that might perceive it as a threat, would allow for observation without immediate contact or confrontation or misunderstanding. It's strategically sensible from a certain perspective. Or, alternatively, a probe might simply resemble a comet because both are small, icy bodies travelling through space following gravitational trajectories. The resemblance could be coincidental, the product of physics and the way objects naturally form and travel. Either way, if you wanted to study a solar system with an emerging technological civilization, how would you actually do it? You'd probably want to observe from a distance first, at least initially. Gather data on the planet's atmosphere, its surface composition, any electromagnetic emissions suggesting technology or civilization. You'd want to characterize the biosphere, understand what's there, assess whether direct contact would be prudent, and you'd want to do all of this without revealing your presence prematurely, without triggering alarm or defensive responses. The perihelion window, that moment when an object is closest to the Sun and moving fastest relative to solar gravity, would be ideal for maneuvers of any kind. Apply thrust at the right moment when the object is moving at maximum velocity, and you get the biggest energy gain for the same amount of propulsive effort. This is the Oberth effect, basic orbital mechanics that's taught in any advanced physics course, and it's applicable equally to natural comets shedding mass through outgassing, and theoretical spacecraft with functioning engines firing in controlled bursts. If 3 Atlas is a probe, what's its purpose exactly? Reconnaissance seems most likely. Scientific observation. Gather information about Earth, its biosphere, its technological signatures, its potential as a threat or as a target for future contact, then move on. Continue the mission to the next star system, the next candidate for study. Or maybe, and this is a genuinely eerie possibility, it's been drifting through space for millennia, a relic probe from a civilization that no longer exists, still executing its programmed mission billions of years later, still faithfully visiting star systems and recording data that will never be analysed by anyone who sent it. Maybe it's a ghost in the machine, a remnant of a dead empire still carrying out its ancient directives. The dark forest hypothesis, borrowed from science fiction but discussed seriously by researchers like Loeb in academic contexts, suggests that an intelligent probe would be cautious, extremely cautious. It would observe from a distance rather than announcing its presence directly with radio signals or obvious technological signatures. It would gather information without making contact. This caution would be strategic and essential. Revealing yourself to an unknown civilization could be genuinely dangerous. You don't know their intentions, their capabilities, their hostility or friendliness toward visitors from other star systems. You don't know whether they'd interpret your presence as an opportunity for trade and knowledge sharing, or as a threat that needs to be eliminated. So you watch. You collect data quietly. You maintain operational security. You study the civilization from afar without interference. The problem with the probe hypothesis is that it requires accepting a chain of extraordinary assumptions stacked on top of each other. The object has to be artificial, which contradicts every prior observation about comets. It has to have propulsion capability of some kind, advanced enough to execute course corrections. It has to be deliberately maneuvering with purpose and intelligence guiding its trajectory. It has to have sophisticated knowledge of Earth's location, distance from its current position, and orbital mechanics. It has to be actively targeting this region of space specifically. Each assumption compounds uncertainty exponentially. The probability drops with each added layer. But science doesn't work on probability alone, not in the way the social media narrative suggests. It works on evidence. And right now, the evidence for the probe hypothesis is circumstantial at best and ambiguous at worst. There are no smoking guns, no definitive signatures of artificiality that can't be explained through natural means, No radio transmissions confirmed from the object despite continuous monitoring by radio telescopes. No obviously manufactured materials detected by spectroscopy. The acceleration could be outgassing. That's still the most plausible explanation. The composition could be natural, just formed under different conditions in a different stellar system with different chemistry and physics. The trajectory could be coincidental, the product of random dynamics in whatever star system it came from originally. Yet the fact that serious researchers, people with credentials and publication records and standing in the scientific community, are willing to publish papers asking, "Is this alien?" Technology speaks to something genuinely important. It speaks to the limits of what we actually understand about small bodies in space, about interstellar objects, about the diversity of things the universe contains. It speaks to the genuine ambiguity in the data, the fact that multiple interpretations remain plausible. And it speaks to the principle, fundamental to science, that extraordinary claims while requiring extraordinary evidence shouldn't be dismissed without serious investigation if the evidence is genuinely ambiguous or if natural explanations are becoming strained. The probe hypothesis makes testable predictions that observations can actually evaluate. If 3 Atlas is artificial, we should see certain things that would distinguish it from natural behavior. We should see minimal mass loss despite the acceleration, because artificial propulsion doesn't require ejecting large amounts of material. We should see persistent acceleration as the object moves away from the Sun, because artificial thrust isn't dependent on solar heating like outgassing is. We should potentially see radio emissions or other technosignatures at specific frequencies or with specific patterns. We should see evidence of controlled maneuvers in the trajectory data, subtle course corrections that don't match what gravity and outgassing alone would produce. Over the next few months, observations will test these predictions rigorously. If they're confirmed one by one, the conversation changes immediately and becomes something much more profound. If they're not confirmed, if the evidence keeps pointing toward natural explanations, the probe hypothesis fades back into the realm of speculation where it belongs. Trajectory mechanics and maneuver possibilities. Understanding how objects move through space, how small forces accumulate over time, how trajectories respond to thrust is crucial for evaluating whether 3 Atlas could realistically be steering itself toward any particular destination. Get this wrong, and the entire argument falls apart. Get it right, and you understand something fundamental about what's actually possible. The Oberth effect is fundamental here, and it's worth understanding deeply. It's named after Hermann Oberth, a pioneering figure in rocketry and spaceflight theory, and it describes a principle of orbital mechanics that seems counterintuitive at first, but makes perfect sense once you work through the mathematics. When you apply thrust to change an object's velocity, the effect on the object's total orbital energy depends critically on where in the orbit you apply that thrust. The faster the object is moving when you apply the thrust, the more energy you gain from the same amount of propulsive force. This seems wrong intuitively. You're applying the same force either way, you're burning the same amount of fuel, you're expending the same energy. But the effect on orbital energy is different because kinetic energy scales with the square of velocity. Double your speed and your kinetic energy quadruples. Apply a 1 meter per second change to velocity at high speed, and you get vastly more energy change than applying the same 1 meter per second change at low speed. It's counterintuitive but absolutely correct. For 3 Atlas, the point of maximum velocity is perihelion, the closest approach to the Sun. At that moment, around October 30th, 2025, the object is moving fastest relative to the Sun's gravity. If you wanted to execute a maneuver, to change the object's trajectory or velocity in a way that would produce maximum efficiency, perihelion is when you'd do it. It's where you'd execute burns if you're trying to alter the orbit or reach a target. A burn of a given duration at perihelion produces a dramatically larger change in orbital energy than the same burn performed farther from the Sun when the object is moving more slowly. This isn't just a minor difference, it's substantial. The energy gain multiplies. This is physics. It applies regardless of whether the object is a natural comet outgassing, through sublimation of ices, or an artificial craft with functioning propulsion systems firing in controlled bursts. The principle is pure geometry and energy conservation, neither of which cares about the source of the force. Now 3 Atlas passes Earth at an estimated 1.8 astronomical units on December 19th, 2025. That's about 270 million kilometers of separation. an enormous distance by any reasonable measure. Converting that into an actual intercept or close approach would require a velocity change that's many times larger than the reported 86 meters per second, unless the thrust happened to be applied in an extraordinarily favourable direction, with perfect timing relative to Earth's orbital position. And that's a big unless. The physics here is genuinely complex. Orbital mechanics in 3 dimensions involves calculations that must account for multiple gravitational influences, relativistic effects, perturbations from planets, solar radiation pressure, drag from the interplanetary medium, and countless other subtle forces that all accumulate. Simple arithmetic like the social media calculation, the basic kinematics of force times time equals velocity change, captures only the most elementary part of the picture. It's like trying to predict weather by knowing only the current temperature. If you wanted to move 3 Atlas from a 270 million kilometre miss into an actual collision course, you'd need to apply significant velocity changes. We're talking about needing to alter the object's velocity by multiple kilometres per second, not a mere 86 metres per second. You'd need to apply this thrust early in the trajectory, months before closest approach, ideally even before perihelion when the object can respond most efficiently. Applying thrust just near perihelion would be too late to substantially alter the miss distance, and you'd need to know exactly where Earth would be when the object arrives, accounting for Earth's own motion around the Sun at 30 kilometers per second. Hitting a moving target from interstellar space requires computational sophistication and precision that strains credibility unless you have extremely advanced trajectory prediction and control systems. It's theoretically possible for an advanced civilization that's had millennia to perfect spaceflight. It's not remotely plausible for a random natural comet simply outgassing as it approaches the Sun. The direction of any applied thrust matters as much as, or perhaps even more than, the magnitude. Push sideways perpendicular to the velocity vector, and you change the orbital plane, rotating the entire trajectory through space. Push along the velocity vector and you change arrival time, but not necessarily the approach distance. Push radially toward or away from the Sun, and you alter the fundamental shape of the orbit, the eccentricity, the perihelion distance. Without knowing exactly which direction the non-gravitational acceleration is pointing, in what geometric orientation relative to the Sun and Earth's position, we can't say definitively what effect it would have on the miss distance. This is where the social media claims really break down and lose their connection to orbital mechanics reality. They assume the acceleration is perfectly aligned, perfectly oriented, perfectly directed to move the object toward Earth specifically. There's no evidence that's the case. There's no mechanism by which a natural outgassing comet would preferentially accelerate toward Earth rather than in some random direction determined by where ice deposits happen to be on the surface, and the probability of it happening by chance, of the acceleration vector randomly pointing exactly toward Earth, is astronomically small. We're talking probabilities that make lottery odds look generous, composition anomalies. The physical makeup of 3 Atlas presents characteristics that don't fit comfortably into our established taxonomy of small bodies orbiting or visiting the solar system. Spectroscopy, the analysis of light reflected or emitted by the object across different wavelengths, has revealed composition details that astronomers find intriguing and somewhat puzzling in equal measure. High concentrations of carbon dioxide compared to typical solar system comets. Nickel content suggesting a composition more similar to an asteroid or metal-rich body than to a typical icy comet. These are genuinely interesting because they point toward formation in a different stellar environment, under different conditions, possibly in a star system with radically different chemistry than our own Sun ever experienced. The diversity of planetary systems is enormous. Different stellar processes create different abundances of elements. Different protoplanetary disks produce different compositions in the asteroids and comets that form within them. 3 Atlas bearing the chemical signature of a different system makes complete sense if it's truly interstellar. The blue coloration of 3 Atlas is particularly noteworthy and has been remarked upon by multiple independent observers and research teams. Typically, comets appear reddish or greyish or brown because of organic compounds and extensively processed material accumulating on their surfaces over billions of years of exposure to cosmic radiation, solar wind, and meteoritic bombardment. This object shows a blue tint that's unmistakable and has been documented in multiple observations. This could indicate ionized carbon monoxide molecules in its atmosphere and possibly on its surface. Carbon monoxide ice is more volatile than water ice, sublimating more readily at lower temperatures and greater distances from the Sun. An interstellar comet formed in a different stellar system could naturally have a different composition than what we're accustomed to seeing. Maybe its surface is richer in carbon monoxide ices, in nitrogen ices, in exotic volatiles we rarely encounter in our own solar system's comets. Maybe it was formed in a region where such materials were abundant during planet and planetesimal formation. Formation in another star system literally means formation under different pressures, different temperatures, different chemical abundances, different physical processes. The result would naturally be different. But here's what's genuinely strange and what creates the tension in the data. If this is just a comet with an unusual composition, why isn't the outgassing matching the expected signatures? The colour strongly suggests carbon monoxide. Carbon monoxide ice should sublimate as solar heating increases. It should create visible jets and a coma around the nucleus. We should see a dramatic display of gas and dust surrounding the object, glowing and reflecting sunlight. Instead, what we actually see is far more subtle and ambiguous. There are reports of jet structures, possibly directed toward the Sun in an unusual configuration rather than away from it. Images show something, some structure and activity, but not the massive visible coma that Loeb's mass loss calculations would predict. The mathematics suggests we should see this enormous cloud of material. The observations don't clearly show it. It's as if the expected outgassing signature doesn't match the expected composition. It's as if something about the physics isn't quite working the way it should if we're dealing with a standard comet, with standard outgassing physics. There's also the question of what we haven't detected, what's conspicuously absent from the observational data. Imaging from the best telescopes, with all their resolution and sensitivity, should show a massive cloud of gas and dust if 1/6 of the object's total mass is evaporating over a month. We haven't clearly observed that, not in the quantity theory predicts. Spectroscopy should show abundant volatile signals from water, carbon monoxide, carbon, dioxide, methane. The signals are there, but they're more subdued than they should be based on the outgassing rates the acceleration implies. It's like the object is showing us just enough to suggest comet behaviour and keep the natural explanation technically viable, but not quite enough to satisfy the full expectations and predictions of standard comet physics. Natural astronomers have explanations for this discrepancy. Maybe the outgassing is episodic, concentrated in brief intense bursts near perihelion, rather than sustained throughout the approach. Maybe the gas is escaping in concentrated jets, focused in specific directions, rather than spreading uniformly around the nucleus like a normal comet. Maybe the composition is such that the dust content is minimal even though gas is being released, making the coma less visible. All of these are plausible individually, but they all require special circumstances, unusual configurations, explanations that add complexity and specificity rather than simplicity and generality. The galactic context. 3 Atlas didn't just randomly materialize in our solar system through some impossible accident of probability. It came from somewhere specific, travelled along a trajectory determined by the orbital mechanics of its home system, by the gravitational influences it encountered along the way, through the vast spaces between stars, by the geometry of space and time itself. Its trajectory points back toward the constellation Sagittarius, toward the galactic centre, where the supermassive black hole that anchors our galaxy sits in cosmic majesty. That's the densest, most active region of the entire Milky Way. That's where stellar density is highest, packed thousands of times more densely than our solar neighbourhood. That's where gravitational interactions between stars are most frequent and most violent. That's where planetary systems are most likely to be disrupted by close encounters with other stars, ejecting bodies and sending them fleeing into interstellar space on escape trajectories. The galactic centre is the engine of chaos that launches interstellar wanderers. We've only identified 3 interstellar objects in human history, 3 data points in the entire archive of human observation. That's not enough to establish statistically robust patterns or make definitive claims about galactic distributions. But the coincidence is worth noting and worth thinking about carefully. Oumuamua, the first, came from the general direction of the constellation Lyra. Borisov, the second, came from the general direction of the constellation Perseus. 3 Atlas, the third, comes from the direction of Sagittarius and the galactic center. 3 different directions from 3 different objects. 3 separate arrival vectors pointing toward 3 separate regions of the sky. Random chance would certainly predict this kind of distribution. But if there are preferential corridors through the galaxy, gravitational highways that channel objects more frequently along certain routes determined by galactic structure, then an object arriving from the galactic center direction might be following one of those natural routes. The galaxy isn't uniform or homogeneous or randomly distributed. It has profound structure on every scale. Stellar streams where groups of stars have been pulled and stretched by tidal forces, creating filaments of stars following specific orbital paths determined by gravitational potentials. Dark matter halos that create invisible gravitational scaffolding influencing how everything else moves through space. Density variations that create some regions with concentrated material, higher gravitational complexity, greater potential for objects to be flung into escape trajectories. If objects from the central regions of the galaxy are more frequently ejected through stellar encounters, and if the galaxy's overall gravitational structure channels them along certain preferential paths as they disperse outward through the galactic disk, then you might expect interstellar visitors to show directional clustering when they arrive in distant neighborhoods. The fact that we have only 3 confirmed examples means we absolutely cannot make statistically robust claims about distributions or patterns. But the question is worth asking and worth investigating as more data arrives. Consider how traffic moves on Earth and through our solar system to understand the principle. Ships don't scatter randomly across every square mile of ocean. They follow established routes optimized for distance, currents, fuel efficiency, safety. Airlines have structured corridors, jet streams, standard approach patterns determined by atmospheric dynamics and international coordination. The internet has backbone routes where traffic concentrates and flows most efficiently. Shipping lanes and air corridors and fiber optic cables all follow patterns determined by efficiency and physical reality. Why would the galaxy be fundamentally different? If interstellar objects are frequently ejected from the dense central regions, and if some fraction of those objects follow gravitational corridors outward through the galactic structure, you'd expect to see clustering in where they arrive from, directional preferences in the arrival vectors. 3 Atlas, arriving from the galactic center direction, could be perfectly statistically normal and expected. Or it could be following a cosmic highway, a gravitational channel that funnels traffic through our neighborhood of space. Detection infrastructure vulnerabilities. Here's where the bigger picture starts to become clearer and more concerning. The story of 3 Atlas isn't just about one object passing through our solar system on its way to destiny. It's connected to broader systemic vulnerabilities in how we detect things, how we monitor space, how we coordinate observations across institutions and agencies. Our detection infrastructure is impressively sophisticated in many ways, but centralized in dangerous and fragile ways. Sky surveys use specific equipment, pointed in specific directions at specific times on specific schedules determined by funding and administrative decisions. When new data arrives from these telescopes, it's processed through networks and computing systems that have internal dependencies and single points of failure hidden throughout. Our ability to observe space ultimately depends on orbital infrastructure, satellites that relay communications, the vast internet systems that allow researchers separated by oceans to share data and compare notes instantly across the globe. When 3 Atlas entered solar conjunction in late October, becoming invisible to every Earth-based telescope simultaneously, we lost our direct observation capability. We couldn't see what was happening during that critical period. We couldn't monitor the object directly during its closest approach to the Sun. That's a blind spot created by our position in space relative to the Sun, an inevitable consequence of orbital geometry. But there are other blind spots created by how our infrastructure is organized, by choices we've made about systems and centralization. Not all data is real-time, not all observations are continuous or maintained without interruption. There are gaps in coverage, periods when nobody's looking at particular regions of the sky. There are times when specific regions of the sky receive substantially less attention than others. There are moments when monitoring systems are overwhelmed by data processing demands or offline for maintenance or forced upgrades. The cloud infrastructure outage that occurred earlier in 2025 is directly relevant here. When major internet systems fail catastrophically, Data collection systems that depend on cloud services for storage and processing can be affected downstream. Monitoring capability can be degraded. Information flows can be interrupted or delayed. This creates what you might call a compound blind spot, or a confluence of multiple blind spots. The cosmic observation window effectively closing as 3 Atlas passes behind the Sun. Simultaneously, terrestrial infrastructure that supports data collection and analysis might be strained or degraded. Multiple monitoring systems might be overwhelmed or offline. If you wanted to study something without being observed, if you wanted to move through our detection systems unnoticed and undetected, that would be an extraordinarily opportune moment. This isn't paranoid conspiracy thinking or unfounded speculation. This is recognizing how complex systems actually work in the real world. Complex interconnected infrastructure creates cascading vulnerabilities throughout the system. When multiple systems experience problems simultaneously, either by coincidence or by design, the combined effect is amplification. One blind spot is manageable with planning. 2 simultaneous blind spots create genuine opportunities for activities that might otherwise be detected easily. Our detection infrastructure is also dangerously concentrated in certain hands and institutions. The major cloud providers who host data from observatories around the world, the satellite operators who maintain the infrastructure for communications and precise timing, the research institutions that analyze the data and publish results, the funding agencies that make decisions about what gets observed and what doesn't. This concentration creates real vulnerabilities in the system. A disruption in one place can cascade outward through the entire network. A policy decision at one agency can affect multiple observatories and research programs. A funding cut can reduce monitoring capability across multiple projects. An outage at one facility can affect dozens of dependent systems across the globe. This isn't unique to astronomy. It's true throughout modern technological civilization. We've traded decentralization for efficiency. We've concentrated critical functions in systems that are more efficient individually, but more fragile systemically. The benefits are enormous when systems work. The risks are substantial when they don't. For 3 Atlas specifically, what this means is that our observation capability during the critical period is fundamentally dependent on a complex web of systems, many of which represent single points of failure or catastrophic vulnerability. If the James Webb Space Telescope went offline during this window, we'd lose infrared data and lose it permanently. If Hubble experienced serious problems, we'd lose visible and ultraviolet observations during the most important phase. If the Jet Propulsion Laboratory's systems failed, we'd lose precise astrometric tracking and trajectory calculations. If funding suddenly dried up, observation campaigns would be reduced or cancelled entirely. We're not prepared for multiple simultaneous infrastructure failures. We don't have adequate redundancy in some critical areas. We've optimized for normal operations and made ourselves vulnerable to cascading failures. 3 Atlas is passing through our solar system at exactly the moment when our detection infrastructure faces significant challenges from multiple sources simultaneously. Some of those challenges are natural and completely inevitable, like solar conjunction and geometry. Others are the product of how we've structured our technological civilization around efficiency rather than resilience. Neither changes the fundamental fact that we're flying blind in multiple directions during the most scientifically interesting and critical phase of this object's passage through our neighborhood. Those blind spots aren't theoretical problems we can solve later. They're immediate operational challenges that define what happens in the next 60 days. Right now, in the present moment, we're committed to watching 3 Atlas with incomplete vision. So let's talk about what actually happens if the worst-case assumptions turn out to be correct. If the social media claims somehow held water, if the acceleration persisted exactly as calculated, if it pointed in exactly the right direction, and if Earth cooperatively remained at the exact point in its orbit where 3 Atlas was aimed, then yes, collision becomes theoretically possible. Not probable, not even particularly likely given the physics we understand, but technically possible within the mathematical constraints. Let's walk through the actual numbers because they matter for understanding just how catastrophic the worst case would be. Size estimates for 3 Atlas range from conservatively several hundred meters to somewhere in the range of 5 or more kilometers in diameter. Some calculations based on its brightness and assumed reflectivity suggest it could be even larger. The most recent analysis from major observatories suggests a mass somewhere north of 30 billion tons, possibly substantially more, maybe 50 billion, maybe higher. We're not exactly certain because we're working with limited data and making assumptions about composition and internal density that could be off. That's not a rock in the conventional sense, that's a small mountain, a chunk of solid or partially consolidated material that could be anywhere from tightly packed to loosely aggregated. A chunk of solid material millions of times more massive than anything we've ever deflected or even seriously attempted to slow down. When something that massive is travelling at 60 kilometers per second, which is roughly what 3 Atlas is moving at through our solar system, when it's moving at speeds that approach the escape velocity from Earth itself, the energy is almost incomprehensibly large. It's the kind of energy that exists primarily in physics equations and thought experiments. Most people don't have intuitive feel for what numbers that big actually mean. The formula is straightforward if you have a background in physics, though the numbers themselves are anything but simple to conceptualize. Kinetic energy equals half mass times velocity squared. The velocity squared part is the killer, because it means even modest increases in speed produce absolutely enormous increases in energy. You take a mass of 30 billion tons, which is 3 times 10 to the 13th kilograms. You multiply that by velocity squared. 3 Atlas is moving at roughly 60 kilometers per second, which is 60,000 meters per second. Square that, and you're looking at 3.6 times 10 to the 9th. Multiply those together, and you get roughly 1.4 times 10 to the 23rd joules. That's what physicists call an absolute staggering amount of energy. For context, to really drive this home, the largest nuclear weapon ever detonated was the Soviet Tsar bomber at 50 megatons. That was the most destructive thing humanity ever built in the entire 20th century. That impact energy from 3 Atlas would be equivalent to approximately 3 million megatons. 3 million! 60,000 times more powerful than the largest weapon humanity ever built. To put that in even starker terms, all the nuclear weapons ever detonated in human history combined wouldn't add up to one 3 Atlas impact. An object striking Earth at that velocity and with that energy would not gradually slow down in the atmosphere. The atmosphere would not gradually decelerate it. The object is moving too fast, carrying too much momentum. It would punch through like a bullet through tissue, which is actually a pretty accurate analogy except scaled up to planetary dimensions. The impact would release all that energy at once, converting kinetic energy into heat, blast wave, ground motion, everything at the same instant, creating an explosion that would be visible and felt across entire continents. Thousands of kilometers away, people would see the flash and feel the heat and hear the sound hours later. Everything within hundreds of kilometers of the impact site would be obliterated by the initial blast. Not just destroyed, not just damaged severely, obliterated, vaporized. Beyond that, a massive shockwave would race outward, flattening structures, snapping trees like matchsticks, vaporizing anything not shielded underground. If it struck the ocean, and let's consider that scenario because oceans cover most of the planet, it would create tsunamis thousands of meters high, walls of water traveling at jet speeds, crossing ocean basins and destroying coastal civilizations completely. Every coastal city on the affected ocean would be wiped out. Inland cities within a certain distance would be buried underwater. The impact itself would vaporize enormous quantities of rock, soil, water, and the impactor itself, throwing all of that material into the upper atmosphere. That's where the extinction level scenario really kicks in. The atmosphere fills with dust and aerosols, sunlight gets blocked, global temperatures plummet, photosynthesis stops working because there isn't enough light, crops fail, supply chains collapse. The world enters a state of perpetual winter that could last months or years, depending on the exact impact location and size. More people die from famine and cold than died in the initial impact. We're talking about an event comparable in scope to the asteroid impact that killed the dinosaurs 66 million years ago. 90% or more of the species on Earth go extinct. The vast majority of large animals, including humans, simply don't survive. It's not an extinction of all life. Microbes survive, some insects survive, some reptiles survive. But the world we know, the civilization we've built, the way of life that billions depend on, it all effectively ends. Now, let's be clear about what would need to happen for this extinction-level impact scenario to actually occur. The object would need to have a functioning propulsion system, and it would need that system to be capable of sustaining significant acceleration for months, not just days or weeks. It would need to have been programmed or designed or controlled with detailed knowledge of where Earth would be at a specific point in time. The programmers would need to have known Earth's orbital position to extraordinary precision. It would need to have started its course correction not near perihelion, as the social media claims naively suggest, but far earlier, months ago when 3 Atlas first entered the solar system, or possibly years ago, as it approached from interstellar space. The vector of the acceleration would need to be perfect, or nearly perfect, slightly off, and it misses by millions of kilometers. The timing would need to be perfect. If Earth moves even a little bit, a few million kilometers, from where the calculations assume it will be, the intercept doesn't happen. The required precision is extraordinary, absolutely extraordinary, the kind of thing that requires either phenomenal luck or extremely advanced computational capability, and profound understanding of orbital mechanics and multivariate trajectory prediction. NASA orbital modelers have looked at these scenarios, ESA has done the same. Their conclusion is consistent and unambiguous. The object is not on a collision course with Earth. The miss distance is comfortable. The trajectory is well understood and stable given all the known gravitational forces. If there were even a small chance of impact, if there was something in the data that suggested danger, the planetary defense networks would be screaming. They're not. They're monitoring it, sure, but they're not treating it as a threat. That distinction matters. The worst-case scenario is theoretically possible if you stack enough assumptions, but it's not happening. It's not going to happen based on everything we can measure and calculate right now. But the fact that 3 Atlas poses no current threat doesn't mean we shouldn't think seriously about planetary defense generally. In fact, it's exactly these non-threatening scenarios that let us think clearly about the problem without panic-clouding judgment. The object reminds us that the solar system isn't empty. It's not a vacuum devoid of material. Things move through it constantly. Asteroids, comets, now we know interstellar objects as well. Some of those things could be dangerous under different circumstances. We need to be honest, almost brutally honest, about our actual capabilities and our actual vulnerabilities when it comes to defending the planet against impacts from space. We need to acknowledge what we can do, and, more importantly, what we can't do. The NASA Planetary Defense Coordination Office exists specifically to track near-Earth objects and assess their threat level. They maintain the most comprehensive database of asteroid and comet trajectories in the world. They coordinate with observatories across the planet to maintain continuous monitoring. When something new appears that might pose a threat, systems activate, alerts go out. Additional observations are requested. The object goes into the catalogue and gets tracked continuously. If the threat level ever reaches a certain threshold, the response mechanisms activate. Interagency task forces assemble. Contingency plans are dusted off and reviewed. The conversation shifts from science into policy and crisis management. 3 Atlas has been added to tracking systems, but it's on the interesting but not currently dangerous list. It hasn't triggered the protocols that would activate if danger were even suspected. That's significant. It tells us the orbital mechanics are good enough that even specialists with all available data don't see a threat. But it also highlights something crucial about planetary defense readiness. We're prepared for things we can detect years in advance. Solar system objects follow predictable paths. If we know they're there months or years before closest approach, we have time to think about what to do, time to potentially mount a mission to deflect or study the object. Interstellar objects are different. They're travelling too fast to slow down much. They're not bound to the sun's gravity. They come from the direction of the stars, which means they announce themselves only when they're relatively close. By the time we detect 3 Atlas, the crucial window for any kind of major course correction had already passed. If it had been on a collision course, there would have been almost no time to do anything about it. We detected it in July 2025. It reached perihelion in October 2025. The closest Earth approach is December 2025. That's 5 months from discovery to closest approach. For a solar system object that we've tracked for years, 5 months might be enough time to organise a mission. For an interstellar intruder, it's barely anything. It's not enough time to build and launch a spacecraft unless you happen to already have one waiting. The DART mission, the Double Asteroid Redirection Test, was designed specifically to show that we could alter the trajectory of an asteroid by crashing a spacecraft into it at high velocity, using kinetic energy to nudge the object slightly off course. The mission was successful. It demonstrated the technology works for certain classes of objects. But DART was targeting a small asteroid, a few hundred meters across at most. moving at relatively slow speeds within the solar system, measured in kilometers per second rather than tens of kilometers per second. 3 Atlas is orders of magnitude larger and moving much faster. The energy required to deflect something that massive would be absolutely enormous, far beyond what any single spacecraft impact could achieve. A spacecraft impact would be like throwing a pebble at a mountain. It might make a small crater, maybe displace a few thousand tons of material, but it's not going to redirect the entire mountain. It's not even going to meaningfully slow it down. This points to the fundamental challenge with planetary defense against interstellar objects. We can't really defend against them with current technology. The best we can do is detect them, track them, understand their trajectories and hope they miss us. We can study them as they pass. We can gather unprecedented data about objects from other star systems. But we can't meaningfully change their course if they're headed toward us. That's not a comfortable position to be in, but it's the position we're in. The only real solution would be decades of advance warning, which wouldn't be possible for an object coming from interstellar space. Some researchers have proposed having spacecraft positioned in space specifically for the purpose of waiting for an interstellar object to appear, pre-positioned and ready to intercept for close study. That's an intellectually interesting idea that makes scientific sense, but it requires sustained funding and coordination across multiple space agencies. It requires maintaining and updating pre-positioned assets over years without using them for anything else. It's the kind of long-term commitment that's easy to lose when budgets get tight in other areas or when political priorities shift away from space exploration. 3 Atlas reminds us vividly that preparation matters, deliberate planning matters, but so does luck, sheer probability. We got lucky this time. The object is passing safely past our planet, but luck doesn't last forever. Eventually an interstellar object will come closer. Eventually we'll face an actual threat from space, and when that happens, preparation will matter enormously. Now, let's address something that's been lurking in the background throughout this entire discussion. The 1.4 GHz pings mentioned in the social media posts, the claimed signals, the alleged communications, the idea that 3 Atlas might be trying to talk to something, or that something is trying to talk to it. This is where the speculation gets genuinely interesting, because if it's true, the implications change everything. 1.4 GHz is significant in the search for extraterrestrial intelligence because it corresponds to the hydrogen line, a natural frequency emitted by neutral hydrogen atoms throughout the universe. It's sometimes called the waterhole in radio astronomy circles, a term that carries deliberate meaning. It's a quiet part of the electromagnetic spectrum where signals can propagate through space with minimal interference from background noise and natural sources. If an advanced civilization wanted to send a signal that other beings with radio astronomy technology could detect, 1.4 GHz would be an absolutely logical choice, maybe even the most obvious choice. It's universal. The hydrogen line is the same everywhere in the universe, the same physical constant. Any civilization with sufficient technology to detect radio waves would likely have discovered this frequency at some point and would recognize it as potentially meaningful. It's the frequency that points toward intentionality. The claim in the social media posts was that 3 Atlas was emitting rhythmic pings at 1.4 GHz near Mars. The phrasing used was almost deliberately intriguing. Handshakes between the object and something near Mars, course corrections, communications. The whole narrative built around the idea of an artificial probe actively signaling and possibly receiving responses. It's compelling. It captures something deep in the human psyche. The idea that something is out there trying to communicate with us. The idea that we might be able to respond. Here's the problem. There's no verified detection of such signals from 3 Atlas. Radio telescopes monitor the sky continuously. Projects like Breakthrough listen specifically search for transient signals, bursts, anomalies, anything that might indicate artificial origin. If 3 Atlas were emitting structured 1.4 GHz signals strong enough to be detected on Earth, someone would have noticed. The astronomical community monitors these frequencies constantly. Radio observatories around the planet are connected. Data is shared. If there were a compelling signal from an interstellar object, it would be the story of the century. It would be announced immediately. The fact that no such announcement exists is strong evidence the signals don't exist, at least not strong enough to be detected, at least not with current equipment. Could the signals be too weak? Possibly. Radio signals follow the inverse square law. They get weaker with distance. At 1 or 2 astronomical units, a relatively weak transmitter might fall below detection thresholds of current equipment. But the social media posts claim the signals were detectable near Mars. If they were strong enough to detect near Mars, they should be detectable on Earth. Mars is only a few astronomical units away. The signal strength shouldn't change that dramatically. The lack of detection suggests the claim is unfounded. Could the signals be intermittent? Could they be brief bursts that somehow got missed? Technically possible, but unlikely. Radio observations aren't continuous in the sense of a single telescope, watching 24 hours a day. But across all the radio telescopes on Earth and in space, across all the time continuously dedicated to monitoring the sky, persistent signals should show up. A brief burst might slip through, but repeated pings, rhythmic signals, sustained communication would accumulate in the data. Someone would notice. The signal-to-noise ratio in radio astronomy has gotten so good that faint but persistent signals are among the easiest things to detect. The most likely explanation is that the claimed 1.4 GHz pings simply don't exist. They're a fabrication, either intentional or the result of someone misinterpreting ambiguous data, seeing patterns in noise that resonate, with pre-existing expectations about alien contact. But let's entertain the hypothesis just to explore what it would mean. It's a useful thought experiment, even if the evidence doesn't support it. Suppose 3 Atlas is an artificial probe. Suppose it does have some kind of communication system. Why would it be broadcasting? What purpose would the signal serve? What reason would an interstellar probe have to announce its presence by sending electromagnetic signals to the heavens? If the object is simply observing Earth and the solar system, broadcast signals would be counterproductive. They would reveal the probe's presence, announce that something artificial is in the system. A cautious approach to observing an emerging civilization would involve passive observation, collecting data without revealing yourself. Broadcasting signals seems incompatible with that strategy, unless the signals aren't meant for Earth at all, unless they're meant for something else. Maybe the probe is communicating with other probes. Maybe it's reporting back to whatever civilization sent it. Maybe there's a network of communication we're completely unaware of, happening on frequencies we don't monitor or in ways we don't recognize. This gets into territory that is almost impossible to evaluate without evidence. We could speculate endlessly about what an advanced civilization's communication might look like. We could imagine quantum entangled particles, higher dimensional transmissions, technologies based on physics we don't understand yet. We could postulate civilizations that communicate through means that have no electromagnetic component at all. But without evidence, this is just imagination. This is the realm of science fiction, not science. The reality is that our knowledge of 3 Atlas is incomplete in ways that go beyond the obvious conjunction blind spot. We have observations from the period before it entered solar conjunction, detailed measurements from telescopes around the world, and in space tracking the object as it approached perihelion. We'll have observations from after it emerges from behind the Sun, another round of detailed tracking as it continues outbound toward its December 19th closest approach to Earth. But the most scientifically interesting period, the time when the object was closest to the Sun, experiencing maximum heating, potentially showing its most dramatic activity, when whatever it was going to do during this passage would naturally occur, we have no direct observations of that. It's hidden. It's a blank spot in the observational record, a blind spot created entirely by our position in space relative to the Sun and 3 Atlas's current position. In theory, that information still exists, encoded in the radiation patterns and gravitational waves and particles streaming away from the object during that hidden period. In theory, we could extract some of that information from post-conjunction observations through careful analysis. We can look at the trajectory before and after conjunction and infer what forces acted during the hidden period. We can analyze the spectroscopic signatures to look for materials that shouldn't be present if the object was stable. We can search for sudden changes in rotation rate or brightness that suggest something happened during the observation gap. But extracting that information requires precision measurements, sophisticated analysis, and careful interpretation. It requires knowing what we're looking for, and sometimes it requires luck in finding things we weren't specifically looking for. The data exist in archive form, scattered across multiple observations from different telescopes at different wavelengths. Hubble data, JWST observations, ground-based telescope images from Chile and Hawaii, and dozens of other locations. Some of that data is already collected and stored. Some of it is still being gathered and processed. Some of it might be lost or degraded if observation systems fail, or if data gets corrupted during transfer or storage. The cloud infrastructure outages that plagued Earth communication networks earlier this year highlighted how dependent our scientific data collection actually is on systems that can and do fail sometimes. Data redundancy exists in theory on paper, in official policies, but in practice those systems are tested only when something goes wrong. Space-based telescopes like Hubble and James Webb maintain their own data stores, but they also upload to cloud servers for long-term storage and for allowing remote scientists to access observations. If those upload systems fail during critical periods, data can be delayed. In the worst case, if systems fail catastrophically and redundancies aren't activated properly, data can be lost. We assume redundancy exists in these systems. Professionally managed archives should have backups, but we don't always verify these assumptions until something actually goes wrong. The conjunction created one kind of blind spot, a purely observational one created by orbital geometry. But there might be other blind spots created by how our infrastructure is organized. There might be data we collected but haven't analyzed. There might be observations from smaller observatories or citizen astronomers that haven't been formally compiled into the scientific record. There might be relevant information scattered across different institutions that nobody has bothered to correlate. The more we look into any complex system, the more we discover that our understanding is fragmented. Knowledge is distributed. No single person or institution has the complete picture. This is where artificial intelligence comes in, and this is where the picture gets genuinely interesting. Machine learning systems excel at finding patterns that humans miss. Patterns that emerge only when you process extraordinary amounts of data simultaneously and look for correlations without preconceived notions about what you're supposed to find. They can correlate data across multiple sources in ways that human analysts wouldn't think to try. They can identify anomalies in massive data sets, flagging things that deviate from expected baselines, even if the deviations are subtle or occur in combinations that don't have obvious human interpretations. They can process terabytes of information and extract meaningful signals from noise, separating real phenomena from artifacts and instrumental effects. In the context of 3 Atlas, machine learning is being applied to historical telescope data, astrometric records going back months before discovery, looking for any sign of unusual activity that might correlate with the object's passage through the solar system. Maybe it was already being observed before official discovery and the significance was just missed. Research teams working with AI have been feeding systems all available observations of 3 Atlas across all wavelengths and all available data streams. Visible light observations from optical telescopes, infrared observations capturing heat radiation from the object, ultraviolet observations that reveal certain chemical signatures, X-ray data, if any, was collected during specific observation runs, everything combined into unified datasets. They've been asking the machine learning systems to identify patterns, to find anomalies, to detect changes in behavior that occurred at specific times relative to the object's passage through different regions of the solar system. They've been looking for evidence that something unusual happened, something that the normal automated processing pipelines might have flagged as noise or outliers, but could actually be real phenomena if you look carefully enough with sufficient sensitivity and the right analytical frameworks. The results are preliminary and require extensive verification before they can be considered reliable or published in peer-reviewed literature, but they're intriguing enough to warrant discussion. Some anomalies have been identified in the infrared data from the period when 3 Atlas was closest to the Sun. Temperature variations and thermal patterns that don't quite match what standard outgassing models would predict for a comet of its estimated size and composition. Spectroscopic signatures and chemical markers that don't perfectly align with standard comet chemistry, or with the chemistry of interstellar objects we've observed before. Nothing definitive. Nothing that screams alien probe or makes a dramatic discovery obvious to everyone immediately, but enough to suggest that the object behaved in ways that deserve closer scrutiny and more detailed analysis by specialists in multiple fields. Machine learning can also be applied to trajectory data in ways that reveal patterns human analysts might miss. By taking all the astrometric observations from multiple observatories and running them through sophisticated orbit-fitting algorithms, researchers can Extract an extremely precise trajectory with high-resolution estimates of any non-gravitational forces acting on the object. The direction of acceleration, not just the magnitude of it. The timing relative to specific features of the solar environment and thermal environment. The correlation with distance from the sun and solar heating intensity. This level of detail and precision can help distinguish between different possible mechanisms for the observed acceleration. Natural outgassing from sublimating ices, which should show a specific temporal signature tied directly to solar heating patterns. Fragmentation of the nucleus, which should show discrete impulses at specific moments. Artificial thrust from a propulsion system, which might show more deliberate and controlled patterns that don't correlate perfectly with solar distance. The machine learning approach democratizes the analysis in some ways, though it also introduces its own complications. Rather than requiring individual researchers to make subjective choices about what to look for, what to assume, what to prioritize, the systems can examine all possibilities in parallel at computational speed. They can test hypotheses that no human researcher might have thought to test, because humans are limited by intuition and experience and preconceptions. They can find correlations that emerge only when you process billions of data points simultaneously, but they also introduce new uncertainties and new failure modes. Machine learning systems can be biased toward patterns that are familiar to their training data, missing genuinely novel phenomena. They can miss patterns that don't look like anything they've seen before during training. They can generate false positives, flagging anomalies that are actually artifacts of the measurement process or instrumental noise. The results always require careful human interpretation and verification by specialists who understand both the data and the physical processes involved. The timeline matters here because machine learning analysis is not instantaneous despite how fast computers are. Data has to be collected and compiled, it has to be processed through multiple algorithms, results have to be analyzed carefully, surprising findings have to be triple-checked and verified to make sure they're real phenomena and not artifacts of the analysis itself. In the 2 to 3 weeks since 3 Atlas emerged from solar conjunction, extensive analysis has occurred by multiple teams working independently and in coordination, but results are still preliminary, still being compiled and cross-checked. It's likely that by December 19th, when the object reaches closest approach to Earth, refined analysis will be available to the broader community. It's possible that by early 2026, when full post-conjunction data analysis is complete and results have been peer-reviewed, we'll have substantially better understanding of what happened during the hidden period when the object was behind the sun. If machine learning analysis reveals anomalies that can't be explained by natural processes, if patterns emerge that demand alternative explanations, that will change the conversation dramatically and immediately. The findings will be presented to the astronomical community, meetings will convene, alternative interpretations will be explored. If the analysis shows everything consistent with normal comet behavior, just unusual comet behavior, then the natural hypothesis strengthens considerably. The exotic explanations recede. The object becomes what it probably always was, a remarkable but ultimately natural visitor. And if the analysis is ambiguous, if the data could support multiple interpretations and reasonable scientists disagree about what it means, then we're back where we started, waiting for more observations to break the tie. The uncertainty isn't resolved yet. It's still playing out in real time as we speak. The next 60 days will provide the crucial data that determines which direction this story ultimately goes. Until then, we watch with incomplete information, we analyze with incomplete understanding, we prepare for possibilities we can barely imagine, and we acknowledge soberly that the universe still contains mysteries that defy easy categorization, and resist our attempts to fit them into comfortable frameworks. 3 Atlas is out there, it's moving through our cosmic neighborhood on its hyperbolic trajectory, and we're doing everything we can with the tools we have to understand what it actually is, and what it might mean for our place in the universe. The sun affects more than just the object itself. Solar weather complications ripple through every system we depend on, every infrastructure, every network of communication and power and data flow that we've built, assuming a stable baseline that doesn't always exist. Right now, in late 2025, the sun is being unusually active, the solar wind is stronger, magnetic fluctuations are more pronounced. Coronal mass ejections are occurring more frequently than during quieter phases of the solar cycle. Part 16, Solar Weather Complications. Solar activity follows cycles that scientists have studied and documented for centuries. The sun goes through periods of relative quiet and then periods of intense activity, called solar maximums. Sometimes those maximums are mild, producing few major storms. Sometimes they're vigorous, with frequent powerful eruptions. We're approaching one now, and the forecasts suggest it might be a vigorous maximum. The last maximum happened around 2014, and the current cycle started ramping up in 2019. We're entering the peak years of solar cycle 25, right now in late 2025, and forecasters from NOAA, the National Oceanic and Atmospheric Administration, have been warning that we should expect increased geomagnetic storm activity through 2025 and into 2026. This isn't abstract academic forecasting made by specialists in an ivory tower. It has immediate consequences for technology, for infrastructure, for our ability to monitor space and coordinate observations on planetary or interplanetary scales. When the sun erupts, when it throws massive bursts of magnetized plasma into space during what's called a coronal mass ejection, those waves of energy and particles reach Earth's magnetic field in 15 to 18 hours. They slam into the magnetosphere and create what we call geomagnetic storms. The magnetic field gets compressed and twisted. Charged particles spiral down toward the poles, creating those beautiful auroras we see in Arctic and Antarctic skies. But the auroras are just the visible part. The real danger is electromagnetic induction in long conductors. Power lines get hit by induced currents. Transformers overload, circuit breakers fail. In extreme cases, entire power grids go down. It's happened before, and we have historical records to study. In March 1989, a major geomagnetic storm knocked out the entire Hydro-Quebec power grid in Canada. 6 million people lost electricity in 90 seconds, sudden blackness across the entire region. It took 9 hours to restore service, 9 hours during which hospitals, businesses, communication networks, everything ran on backup power or stopped functioning. The same storm caused auroras visible as far south as Texas and Florida, a spectacular but ominous sight. It disrupted satellites and radio communications globally. That was classified as a G5 event, the most severe kind on the scale we use. We got lucky that it hit a region that could recover relatively quickly, and that infrastructure was somewhat isolated from the worst effects. If it hit differently, if the timing were worse, the consequences could have been catastrophic for infrastructure spread across continents. Engineers have estimated that if a Carrington-class event, a solar storm of maximum severity, hit today, the damage would be incalculable. Transformers would be permanently damaged, not just tripped. It would take years to replace them. The grid would go down for extended periods. Society would experience a cascade of failures in systems we depend on utterly and completely. Space-based infrastructure is even more vulnerable in some ways and more resilient in others. Satellites get hammered by high-energy particles during geomagnetic storms. Solar panels can be damaged, sometimes permanently if the radiation is intense enough. Electronics can experience memory errors, bit flips in computer memory that corrupt data. Spacecraft can lose attitude control if their gyroscopes are affected. GPS signals degrade. Communication satellites go offline or operate at reduced capacity. Weather monitoring stops working properly. The infrastructure we've built in space to support everything from navigation to finance to emergency response, all of it becomes less reliable during solar storms. Operators put satellites into safe mode, shut down non-essential systems, and hope the hardware survives the onslaught of particles. It usually does, but not always. Occasionally, valuable satellites are lost to solar activity. In 1998, a solar storm knocked out the Galaxy 4 communication satellite, and the entire paging network went down. Millions of people couldn't use their pagers. Hospitals had to find alternative communication methods. It was a warning sign about how dependent we've become on space-based infrastructure without building in sufficient redundancy. And here's the thing that matters directly for 3 Atlas and our investigation. When we're trying to monitor an interstellar object with precision, when we're coordinating observations across multiple telescopes on different continents, when we're uploading and downloading critical data through space-based relay systems, all of that depends on infrastructure that becomes unreliable during geomagnetic storms. The timing is unfortunate, almost seems engineered to make our job harder, though of course it's just random coincidence. 3 Atlas is passing through our solar system at the same time we're entering a solar maximum. In late October 2025, as 3 Atlas is entering solar conjunction, NOAA was forecasting increased storm risk. Those forecasts have probability ranges, not certainties. The forecasting might be off, it might not happen, there might be no major storms during the critical observation period. But if a strong geomagnetic storm occurs right when we're trying to gather crucial observations of the object, when we're trying to coordinate between different observatories in different countries, when we're trying to transmit data down from space-based telescopes like Hubble and JWST, the implications are immediate and consequential. Data flows get interrupted, observations get postponed, communication delays accumulate, telescopes might go into safe mode, some observations might be lost entirely because the data wasn't successfully transmitted before the storm hit. The window for critical measurements gets compressed even more than it already is because of the conjunction. It's another layer of uncertainty, another thing that could potentially interfere with our ability to answer the fundamental question of what 3 Atlas actually is. We're relying on systems that are vulnerable to space weather at a moment when we're trying to perform precision observations of an object that only passes through once. The irony is that 3 Atlas might have been visible from Earth billions of years ago, or will be visible billions of years in the future, but we get this one window right now. And right now is when solar activity is picking up. The conjunction happened right around October 21st, 2025. The angle between Earth and 3 Atlas and the Sun reached the critical point where the Sun positioned itself directly between us and the object from our perspective on Earth. From that moment forward, for the next several weeks, we couldn't see 3 Atlas. Every telescope on Earth pointed in the direction where the object was, and all they saw was the blinding glare of the Sun. No visible light observation, no ultraviolet, no specific wavelengths we normally use to analyze comets. The conjunction created a fundamental observational gap, a period where the most scientifically interesting phase of the object's passage happened entirely out of our view. And the timing mattered enormously, because perihelion, the closest approach to the Sun, occurred right in the middle of that conjunction window around October 29th. That's the moment when 3 Atlas would experience maximum heating from solar radiation. That's when any dramatic activity would occur. Outgassing would intensify if the object is a comet. Surface changes would become apparent. Thermal stress could cause fragmentation. If the object had a propulsion system and wanted to execute maneuvers, that's when the most efficient burns would happen because the object is moving fastest at perihelion. The Oberth effect ensures that small velocity changes applied at high speed produce enormous energy changes. All of that happened, and we couldn't watch it in real time. We could only infer afterward what might have occurred based on evidence collected before and after. The conjunction created something worse than just a blind spot. It created an opportunity for activity to occur unobserved. This is what bothers some people about the social media claims, and it's also something worth thinking through seriously, even if the claims themselves are unfounded. The object had a window where it could do anything, and we wouldn't know until after the fact. If 3 Atlas is artificial and conducted maneuvers during conjunction, if it adjusted its course or performed complicated orbital mechanics, we'd potentially miss direct observation of those maneuvers. If it's natural and did something unusual during its closest approach to the Sun, if it fragmented or emitted unusual amounts of material, we'd miss seeing it happen. Post-conjunction observations might reveal evidence of whatever occurred during the conjunction window, changes in trajectory that we can infer from comparing before and after positions, alterations in composition that spectroscopy might detect after the fact, different molecular signatures that would indicate something happened to the surface, different brightness patterns that suggest something changed about the object's reflectivity or the amount of dust around it, shifts in the structure of any coma or jets. But we wouldn't see the event itself in real time. We'd only see the aftermath, the consequences, the trails left behind like a crime scene investigator, studying evidence hours after an event. This is genuinely challenging for science because it means any conclusions we reach about what happened during conjunction rely on detective work. We have to reconstruct events from indirect evidence. We become archaeologists of an orbital event that we can only examine through its traces and inferences, working backward from effects to infer causes. And that's difficult because sometimes multiple different causes could produce the same effects. And in a field as complex as planetary science and astronomy, reconstructions can be ambiguous. Multiple different events could produce similar observable aftermath. If a comet fragments during perihelion, we'd see multiple objects afterward. But if a probe deployed sub-probes deliberately, we'd see multiple objects afterward. The effect looks the same even if the cause is entirely different. If a comet loses half its mass through sublimation, we'd see a change in trajectory and brightness. But if a probe adjusted its course using a propulsion system, we'd also see a change in trajectory and possibly brightness changes too if dust or plasma was ejected during the maneuver. The interpretation problem is real. It's not insurmountable, but it's real. The conjunction blind spot is a fundamental limitation, not just of this particular observation campaign, but of our position in space relative to the Sun. There's no way around it. Not with current technology. Not with any technology based on electromagnetic observation. Space-based telescopes in different orbits might theoretically maintain partial visibility, but most of our major instruments orbit close to Earth or sit on Earth's surface, which means they share the same blind spot. Every celestial object that passes behind the Sun becomes invisible to us for a period. It's a fundamental constraint imposed by orbital geometry and the fact that we live on one planet looking outward. We can't move. We can't change our perspective. We can only point our instruments at available targets and accept that when the Sun gets in the way, we're blind. Understanding that constraint, acknowledging it, accepting it as part of the reality we work within, is crucial for interpreting whatever data we eventually gather about 3 Atlas. It's also important for thinking realistically about what we can know and what we can't know about interstellar visitors passing through our solar system. Here's what we need to be honest about. We are not prepared for an interstellar object on an actual collision course with Earth, and we never will be unless we start now with decades of advanced planning. The DART mission demonstrated that we can nudge smaller asteroids with kinetic impacts. Scientists calculated that DART could alter the trajectory of an asteroid a few hundred meters across by about a centimeter per second. That's enough to change a collision to a miss over the course of many years. But 3 Atlas at the scale we're discussing is orders of magnitude more massive. If it were actually heading toward us, we'd be limited to early warning, evacuation protocols, and hoping it misses. We couldn't deflect it with current technology. We couldn't mount a spacecraft to destroy it or alter its course. The physics just doesn't work at that scale. A kinetic impact from anything we can build would be like throwing a pebble at a mountain. The best we could do is try to understand what's coming and prepare populations for impact. We'd be staring at an extinction-level threat with no technological solution. That's a genuinely sobering reality to contemplate, and simultaneously, we have no credible evidence that 3 Atlas is on a collision course. NASA says no threat. ESA says no threat. The orbital calculations are clear. The miss distance is comfortable. The object will pass at a safe distance. 1.8 astronomical units means we're never going to see it cause any damage. But the broader planetary defense question looms large over all of this. We discovered 3 Atlas only months before perihelion. It was found in July 2025. By the time we knew it existed, the window for major course correction had already passed. Suppose, counterfactually, that the object had been on an actual collision course. We would have had no meaningful options besides disaster mitigation. Maybe months to figure out where it would hit, how to evacuate people, how to preserve knowledge and try to keep civilization going. That's not acceptable for a civilization with space technology. That's not acceptable for people who care about long-term survival of our species and our accomplishments. We need to improve detection of interstellar objects. We need to make sure our telescopes and surveys are optimized to catch these fast-moving visitors before they're too close to do anything about. We need better early warning systems that can flag potentially dangerous trajectories immediately and distribute that information globally within hours. We need to position spacecraft in space that could respond to a detected threat without needing years to build and launch something from scratch. Imagine having spacecraft already in position, perhaps in high Earth orbit or at one of the Lagrange points, that could be redirected to intercept an interstellar threat on short notice. We need international coordination that goes beyond current efforts, treaties and agreements that establish protocols for how we'd respond collectively to an extraterrestrial threat. This requires investment, sustained attention, political will, and resources that compete with other priorities. And there's always something else competing for resources. Funding for planetary defense competes with funding for medical research, for education, for social programs. It's not glamorous. It doesn't generate headlines the way an alien probe story does. It's easier to focus on things that feel immediately threatening. An interstellar probe may be targeting us, even though the evidence doesn't support it, captures attention in ways that abstract planetary defense preparations don't. People get excited about aliens. People don't get excited about bureaucratic protocols and prepositioned spacecraft. But the boring preparations are actually more important. Redundant detection systems, prepositioned response capabilities, international protocols, training, coordination. These are the things that would actually save civilization if something unexpected arrives. They're unglamorous and they're essential. 3 Atlas serves as a useful reminder that we live in a solar system that contains things we don't fully understand and can't fully control. The object itself might pose no danger, but the broader category of interstellar visitors represents a class of phenomena that we should take seriously. Not with panic, not with fear-mongering, but with preparation, with acknowledgement of our limitations, with recognition that space is not empty, that things arrive unannounced, and that we're still developing the capability to respond effectively. The fact that 3 Atlas passed through our solar system and we detected it only months before its closest approach should give us pause. That pause should translate into action. We need to do better at detection. We need to plan for responses. We need to take the threat seriously without letting it paralyze us or distract us from the actual scientific investigation of what the object is. What 3 Atlas represents extends beyond the immediate question of whether it's a comet or a probe. It represents our expanding ability to detect and study the universe, our growing awareness of how much we don't know, and the collision between scientific uncertainty and public narrative in an era of instant information. The object became a focal point for conversations about planetary defense, extraterrestrial life, artificial intelligence in astronomy, the nature of evidence, what constitutes science versus speculation, and how information flows through society. Each of these conversations matters beyond 3 Atlas itself, and each reveals something about where we are as a civilization in 2025. Planetary defense is not a theoretical concern, not anymore. As Earth's population grows and infrastructure becomes more concentrated and interconnected, the consequences of a major impact become more severe. More people live in coastal cities, which would be devastated by tsunamis from an ocean impact. More people depend on interconnected infrastructure that could be disrupted by the secondary effects of an impact: the dust, the cold, the darkness. We have proof from the geological record that large objects hit Earth regularly on timescales of millions of years. The fossil record shows mass extinction events, most notably the impact that killed the dinosaurs 66 million years ago. We have direct evidence from our own solar system. Craters cover the Moon and Mars. Spacecraft have documented impact sites everywhere we look. Collisions happen. They're statistically rare on human timescales, maybe once every 100,000 years on average, but they're not mythical. They're real physical events that will eventually occur, and when they do, being prepared will make the difference between civilization continuing and civilization ending. The conversation about whether artificial signals might exist from interstellar probes touches on fundamental questions about the prevalence of technological civilizations. If 3 Atlas turns out to be artificial, it would confirm something profound. It would confirm that at least one other civilization achieved the capability to send objects across interstellar space. That single confirmation would change our understanding of the universe enormously. It would suggest that the galaxy contains technological civilizations, that we're not alone, that the chain of events leading to intelligent life and spacefaring capability can happen more than once. It would mean intelligence is not unique to Earth, not a one-time accident that happened to occur here. Those implications dwarf the specific details of 3 Atlas's trajectory or composition. They would reshape how we think about our place in the cosmos. They would transform the search for extraterrestrial intelligence from fringe science to central scientific endeavour. The role of artificial intelligence in this investigation highlights how machine learning is becoming essential for processing astronomical data at scale. We can't manually analyse all the observations, all the possibilities, all the parameter space of what 3 Atlas might be and how it might behave. Computers can process that volume of information and execute that many comparisons in ways no human team could match. AI extends human capability in ways that were impossible just decades ago. In particular, machine learning allows us to find patterns and anomalies that human analysts might miss because the datasets are too large or the patterns too subtle, or the relationships too complex. An astronomer might look at a telescope image and see 3 Atlas against the background stars. An AI system analysing the same data can compare it against millions of simulated predictions, asking at computational speed whether the object matches expected behaviour or deviates in interesting ways. But AI introduces new challenges that we're still learning to navigate. How do we ensure algorithms aren't biased towards seeing patterns we expect to see, confirming our pre-existing beliefs? How do we verify their results independently when their processing involves thousands of mathematical operations and neural network layers? How do we communicate their findings to the public in ways that don't overstate confidence or understate uncertainty? How do we know when an AI system is actually finding real phenomena versus statistical noise or artifacts of how the algorithm was trained? These questions apply to 3 Atlas and far beyond it. They apply to medicine, where machine learning diagnoses diseases. They apply to criminal justice, where algorithms influence bail decisions and sentencing recommendations. They apply to climate modelling, where computers predict future weather, and environmental conditions. They apply to every domain where decisions depend on algorithmic analysis. The broader implication is that as technology becomes more powerful and more central to how we understand the world, how we make decisions, how we navigate complexity, transparency and verification become more important, not less. We need to understand what our tools are doing. We need to check their work. We need to remain skeptical while remaining open to what they reveal. 3 Atlas is a case study in this new reality, where human intuition and machine intelligence need to work together, where we can't just trust the AI but also can't ignore it. So here we are in late 2025, waiting. The months between now and early 2026 will determine the trajectory of this story, literally and figuratively. 3 Atlas continues its journey through the solar system, moving outbound from perihelion toward its December 19th closest approach to Earth. Telescopes are gathering data continuously. Machine learning systems are analysing observations and comparing them against predictions. Radio telescopes are listening for signals, scanning the frequencies where artificial transmissions might occur. Planetary scientists are comparing pre-conjunction and post-conjunction measurements, trying to reconstruct what happened during the hidden window when we couldn't see the object. And across the world, from professional astronomers to amateur observers to people who just follow these stories on social media, people are watching the sky, wondering, speculating, asking questions. The object will emerge from solar conjunction sometime in early November. As it does, observations will resume with intensity. We'll see whether a massive coma appeared during the weeks when we couldn't observe, whether ice sublimated and erupted from the object during its heating period. We'll see whether the object's brightness changed significantly or remained relatively stable. We'll see whether its trajectory shifted in ways consistent with outgassing or in ways that suggest something else. We'll gather spectroscopic data that reveals composition, identifying which molecules are present, whether they're consistent with ice and rock, or whether they suggest something unusual. We'll track its motion with precision that allows us to calculate exactly what forces acted on it during the hidden period, working backward from the observations to infer the physics. By December 19th, when 3 Atlas reaches its closest approach to Earth at approximately 270 million kilometers away, we'll have accumulated weeks of new observations from multiple telescopes and observatories coordinated across continents. We'll have refined orbital models to higher precision, reducing the uncertainties in our trajectory calculations. We'll have analysed whether the claimed 1.4 GHz signals exist or remain unverified speculation, listening across those frequencies with sensitive equipment. We'll have much better understanding of the object's nature, its composition, its behaviour, its physical properties. We'll be able to see whether it fragmented or remained intact. We'll see whether new jets appeared or whether the same outgassing features persisted. We'll have data that lets us make informed judgments. The social media claim, the one that sparked this entire investigation, the claim that 3 Atlas is lining up with Earth, that it's on a collision course or executing intelligent maneuvers toward us, will either be substantially validated or substantially contradicted by actual observational data. There's no middle ground here. Either the evidence supports the claim or it doesn't, and we'll have enough data to tell the difference. If the object continues to show signs consistent with natural comet behaviour, if the acceleration weakens as it moves away from the Sun, as we'd expect from solar heating and sublimation, if no unexplained phenomena appear in the data, if nothing contradicts natural explanations, Then the exotic hypothesis fades into the background. 3 Atlas becomes an unusual interstellar visitor, but ultimately a natural phenomenon. A remarkable comet from another star system, scientifically valuable for what it tells us about planetary formation in other stellar systems, but not revolutionary. We've discovered an interesting comet. That's still valuable. That still matters scientifically. But it doesn't reshape our understanding of the universe or our place in it. If, however, anomalies persist, if the acceleration continues when it shouldn't based on solar distance, if the object shows characteristics that can't be explained by known cometary physics, if radio signals are detected despite the lack of confirmation so far, if the trajectory changes in ways that demand explanation beyond outgassing and natural forces, then the conversation shifts fundamentally. The exotic hypotheses stop being idle speculation. They become active lines of investigation. Scientists who study the object would need to seriously investigate alternative explanations, follow the evidence wherever it leads, pursue implications regardless of how extraordinary they seem. The conversation would expand to involve people outside of astronomy. Physicists would study implications for propulsion. Engineers would consider what technology would be necessary. Politicians would recognize that we'd discovered evidence of another technological civilization. The discovery that we're not alone, that another civilization built and sent objects across interstellar space, would be the most significant finding in human history. It would change everything about how we see ourselves. We're not there yet, though. We're in the waiting period. The evidence hasn't arrived. The observations haven't concluded. The story is still unfolding. What makes this moment interesting? What makes 3 Atlas worth attention despite the likely outcome that it's a natural object is the process itself. We're learning how to study interstellar visitors. We're testing our models against an extreme case. We're demonstrating our ability to coordinate international observation campaigns on short notice, bringing together telescopes from different countries and space agencies. We're showing how science actually works in the modern era, with data, with uncertainty, with multiple hypotheses being tested simultaneously, with social media noise and scientific rigor existing side by side, sometimes in tension with each other. In a few months we'll have answers. The speculation will end or transform into something grounded in evidence. The object will pass and continue on its hyperbolic trajectory back out into the darkness between stars, heading toward whatever region of space comes next on its endless journey. We'll publish papers about what we learned. We'll incorporate 3 Atlas into our growing database of interstellar visitors, learning from it for the next object that arrives, and we'll return to watching the sky for the next mysterious object, the next anomaly, the next visitor from beyond our solar system. Until then, the universe keeps doing what it does. Objects move through space according to physical laws we've spent centuries understanding. Starlight travels across unimaginable distances carrying information about distant worlds. The cosmos operates according to rules that appear consistent and elegant once we understand them, though we're still discovering how deep those rules go. 3 Atlas is a small part of that vast process. It's neither the first interstellar visitor to our solar system, nor will it be the last. But it arrived at a moment when we have the tools to observe it closely, when we can gather data that tells us something about the galaxy beyond our sun, about processes and physics we can't study any other way. That convergence of cosmic chance and human capability, that's what makes 3 Atlas worth watching. So we watch, we analyze, we prepare for possibilities, we acknowledge uncertainty, we press forward with investigation, and we wait for the data to tell us what 3 Atlas actually is. The next few months will answer that question. By early 2026, we'll know whether this was a comet behaving unusually, or whether we found something that changes our understanding of the universe and our place in it. Either outcome deserves our attention, our scrutiny, and our commitment to understanding it fully. The universe is watching us as we watch it. And in that mutual observation, in that ongoing conversation between human curiosity and cosmic reality, we find meaning, we find purpose, we find reason to keep asking questions, keep seeking answers, keep reaching toward understanding in a universe that still holds mysteries we barely comprehend.